Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on linear algebra, chapter Eigenvalues and Eigenvectors, lecture number 3, in which I will prove some theorems on eigenvalues. Now, we prove a theorem. Theorem is the matrix A and its transpose A prime have same eigenvalues. Now we prove this. Let A and B be two square matrices of same order, then A plus B whole transpose equal to A transpose plus B transpose. This is number 1. Ka whole transpose equal to Ka transpose, where K is a scalar. This is number 2. Let lambda be the characteristic root of A. Then A minus lambda I unit matrix determinant equal to 0. This is number 3. Since A minus lambda I whole transpose equal to A transpose minus lambda I transpose, this equal to A transpose minus lambda I using 1 and 2. Also I transpose equal to I. Since determinant of A equal to determinant of A transpose, this is number 4. Therefore, A minus lambda I determinant equal to A minus lambda I whole transpose determinant using 4. Therefore, determinant of A minus lambda I equal to determinant of A transpose minus lambda I transpose equal to A transpose minus lambda I. Therefore, determinant of A minus lambda I equal to 0 implies that A transpose minus lambda I determinant equal to 0. Therefore, lambda is a characteristic root or eigenvalue of A transpose. Therefore, if lambda is a characteristic root or eigenvalue of matrix A, then lambda will be the characteristic root or eigenvalue of A transpose, that is the matrix A and its transpose have same eigenvalues. Proved. Now we prove the next theorem. Next theorem is if K is a scalar, then the characteristic roots of K multiply A are K times the characteristic roots of matrix A. Now we prove this. Let A be a square matrix of order n. Lambda be the characteristic root of A, then characteristic equation will be A minus lambda I determinant equal to 0. This is number 1. Since number 1 is a polynomial equation of degree n, therefore we get n roots from 1. These roots are lambda 1, lambda 2, lambda n, which are known as characteristic roots of matrix A. Therefore, determinant of A minus lambda I equal to 0 implies that lambda 1 minus lambda multiply lambda 2 minus lambda lambda n minus lambda equal to 0. This is number 2. Let alpha be the characteristic root of Ka, where K is a scalar. Therefore, characteristic equation of Ka will be determinant of Ka minus alpha I equal to 0 implies that we take common K, A minus alpha by K I determinant equal to 0 implies that K to the power n determinant A minus alpha by K I determinant equal to 0, since Ka determinant equal to k to the power n determinant of A implies that determinant of A minus alpha by ki equal to 0. This is number 3. Comparing 2 and 3, we get here A minus lambda I equal to 0 implies that lambda 1 minus lambda multiply lambda 2 minus lambda multiply lambda n minus lambda equal to 0. In place of lambda we have alpha by k. So lambda 1 minus, in place of lambda we write alpha by k. Lambda 2 minus alpha by k multiply lambda n minus alpha by k equal to 0 implies that 1 by k to the power n. Here k lambda 1 minus alpha, k lambda 2 minus alpha multiply k lambda n minus alpha equal to 0. We take common k from first bracket, second bracket and nth bracket. 1 by k to the power n implies that k lambda 1 minus alpha, k lambda 2 minus alpha multiply k lambda n minus alpha equal to 0. This is number 4. Here we see that right side is 0. So if this first bracket equal to 0, then alpha equal to k lambda 1. If second bracket is 0, then alpha equal to k lambda 2. And in this way alpha equal to k lambda n. Therefore alpha equal to k lambda 1 comma k lambda 2 comma dot k lambda n, and alpha be the characteristic root of Ka. Therefore characteristic roots of Ka are k times characteristic roots of matrix A. Proved. Now we prove the next theorem. Next theorem is if lambda 1, lambda 2 dot lambda n are characteristic roots of A, n by n square matrix A, and k is a scalar, then characteristic roots of A minus ki, I be the unit matrix, are lambda 1 minus k, comma lambda 2 minus k, comma dot lambda n minus k. Now we prove this. Given that A is a square matrix of order n, let lambda be the characteristic root of A, then characteristic equation will be determinant of A minus lambda I equal to 0. This is number 1. Given that lambda 1, lambda 2, lambda n are characteristic roots of A, then A minus lambda I determinant equal to 0 implies that lambda 1 minus lambda multiply lambda 2 minus lambda multiply lambda n minus lambda equal to 0. This is number 2. Let alpha be the characteristic root of A minus ki, where k is a scalar, implies that characteristic equation of A minus ki will be determinant of A minus ki minus alpha I determinant equal to 0, implies that A minus k plus alpha I determinant equal to 0. This is number 3. Comparing 2 and 3, we get here determinant of A minus lambda I equal to 0. In place of lambda, here we have k plus alpha. So here we write in place of lambda k plus alpha. Lambda 1 minus k plus alpha multiply lambda 2 minus, in place of lambda we write k plus alpha multiply lambda n minus k plus alpha equal to 0, implies that lambda 1 minus k minus alpha multiply lambda 2 minus k minus alpha multiply lambda n minus k minus alpha equal to 0, implies that alpha equal to lambda 1 minus k comma lambda 2 minus k comma lambda n minus k. Alpha be the characteristic root of A minus ki. Therefore, characteristic roots of A minus ki will be lambda 1 minus k, lambda 2 minus k, comma lambda n minus k. Proved. Now we prove the next theorem. Next theorem is if lambda 1, lambda 2 lambda n are characteristic roots of A n by n square matrix A and k is a scalar, then characteristic roots of a plus ki are lambda 1 plus k, lambda 2 plus k, lambda n plus k. In previous theorem, here we had minus sign. Here also minus, here also minus, here also minus. So, similar to previous theorem, given that A is a square matrix of order n, lambda is a characteristic root of A, then characteristic equation will be determinant of A minus lambda I equal to 0. This is number 1. Given that lambda 1, lambda 2, lambda n are characteristic roots of A, then determinant of A minus lambda equal to 0 implies that lambda 1 minus lambda under bracket multiply bracket lambda 2 minus lambda multiply bracket lambda n minus lambda equal to 0. Let alpha be the characteristic root of A plus ki, where k is a scalar, implies that characteristic equation of A plus ki will be here determinant of A plus ki minus alpha I equal to 0. Here we will get A minus alpha minus k I determinant 0. Therefore, here comparing 2, in 2 we have A minus lambda equal to 0 implies that lambda 1 minus lambda multiply lambda 2 minus lambda multiply lambda n minus lambda equal to 0. Here similar thing, in place of lambda we have alpha minus k. So in place of lambda we write alpha minus k. Here alpha minus k, here alpha minus k, here alpha minus k. So we write here lambda 1 plus k minus alpha, here lambda 2 plus k minus alpha, here lambda n plus k minus plus minus alpha, implies that alpha equal to lambda 1 plus k, lambda 2 plus k, lambda n plus k. Therefore, characteristic roots of A plus ki will be lambda 1 plus k, lambda 2 plus k, lambda n plus k. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button. And if you have not yet subscribed my YouTube channel, then please subscribe my YouTube channel. Thank you.